Somewhere beneath the modern Atlantic Ocean, there is a mountain range longer than the Andes, the Rockies, and the Himalayas combined. Almost nobody has ever seen it, and it exists because the planet split open. The world was not always divided into continents. For a long stretch of Earth's history, nearly every major landmass was fused into a single supercontinent called Pangea. Forests stretched across thousands of uninterrupted miles. Animals could walk from what is now Africa into what is now South America without ever seeing an ocean. Then the ground began to tear apart. Not suddenly, not violently at first, just fractures spreading slowly through the crust as molten rock pushed upward from below. The Atlantic Ocean did not exist yet. India was still attached to Antarctica, and the continents beneath the modern world were beginning the longest separation in Earth's history. The coastlines of South America and Africa still carry the evidence. Their rock layers match, their fossils match. Even entire mountain chains line up when the continents are placed back together, and the process never stopped. The ground beneath your feet is moving right now at roughly the speed your fingernails grow. The Himalayas are still rising. The Atlantic is still widening. East Africa is slowly splitting apart into a future ocean that does not exist yet. Tonight, we follow the slow destruction of the largest landmass Earth has ever assembled and the chain reaction that turned one world into the planet we know now. Before we do, if you enjoy content like this, hit the like button and subscribe, and let me know in the comments, is it late where you are right now, or are you starting your day with this? Now, let's step back into the world before the continents separated. A continent feels permanent when measured against a human life. Mountains appear fixed, coastlines seem settled into place. The stone beneath a city can survive longer than entire civilizations. Yet beneath that appearance of stability, the surface of Earth behaves more like drifting ice on a dark sea than a motionless shell of rock. The outermost skin of the planet is fractured into enormous plates, roughly 15 major and minor sections, moving in slow silence across the globe. Some slide apart, some grind sideways, others descend beneath one another and vanish into the mantle below. Together they form the lithosphere, a rigid outer layer extending roughly 100 kilometers downward before meeting softer, hotter rock beneath it. That deeper region, called the asthenosphere, does not flow like liquid water, yet over immense spans of time it bends and circulates slowly under pressure and heat. Far below the crust, energy still leaks outward from Earth's interior, some of it left over from the planet's violent formation billions of years ago. That heat drives convection through the mantle, carrying rock upward in some regions and downward in others. The tectonic plates ride these currents with almost imperceptible patience, moving no faster than growing fingernails. Among the known worlds of the solar system, Earth appears unusual in maintaining this restless surface. Mars preserves ancient scars from long extinct volcanic systems. Venus may still hold internal heat, but its crust behaves as a single stagnant shell rather than a mosaic of moving plates. Earth alone seems to possess the delicate balance required for long-term tectonic motion. Water likely plays a central role, slipping into minerals, weakening rock deep below the surface, and allowing entire plates to descend and recycle. Not all crust behaves the same way. Continental crust is thick, ancient, and relatively buoyant, difficult to destroy once formed. Oceanic crust is thinner, denser, and constantly renewed. New seafloor rises along underwater ridges, while older crust sinks back into the mantle at subduction zones. The ocean floor therefore remains geologically young, while fragments of continental crust preserve some of the oldest surviving rock on the planet. Pangea emerged from this machinery, but it was not the first world spanning landmass Earth assembled. Long before its existence, earlier supercontinents formed and broke apart in cycles stretching deep into geological time. Rodinia existed more than 1 billion years ago. Before that came Columbia, sometimes called Nuna, assembled nearly 1.8 billion years in the past. Each gathered the continents together before tectonic forces slowly tore them apart again. Geologists call this repeating rhythm the Wilson cycle, the gradual opening and closing of oceans across hundreds of millions of years. Continents collide, mountains rise, oceans vanish, then new fractures appear, and the process begins again. Around 335 million years ago, earlier landmasses finally merged into the supercontinent, later named Pangea. For a time, nearly all major continental crust rested together as one connected world. But the same forces that assembled it were still moving beneath the surface, carrying heat upward through the mantle, pressing quietly against the underside of the crust, preparing the slow separation that would reshape every ocean, climate, and living ecosystem that followed. Seen on a modern globe, the continents appear scattered almost casually, separated by broad oceans and curved coastlines. But if the pieces are drawn back together slowly, the shape that emerges is not neat or circular. Pangea resembled a vast crooked crescent, a rough horseshoe wrapped around an interior sea that breathed tropical warmth into the center of the supercontinent. That sea was the Tethys Ocean. Its waters occupied the concave opening within Pangea, stretching across regions that would one day become the Mediterranean basin, the Middle East, and the uplifted stone of the Himalayas. Warm currents drifted through shallow continental shelves, rich in marine life, while carbonate sediments accumulated quietly on the seafloor, destined millions of years later to rise into mountain summits far above sea level. The supercontinent itself extended across astonishing distances, from the frozen reaches of what is now Siberia to the forests and glacial plains of Antarctica. Pangea stretched nearly pole to pole, spanning roughly 12,000 miles. Such scale altered wind, rainfall, and seasonality across the entire planet. The curvature of Earth became visible in the geography itself, with coastlines and climate zones bending across immense, uninterrupted land. Geologists often divide Pangea into two immense regions. In the north lay Laurasia, containing the ancestral crust of North America, Europe, and much of Asia. To the south rested Gondwana, a far older southern assemblage including Africa, South America, Antarctica, Australia, Madagascar, and India. Long before they collided, these continental masses had traveled separate geological paths for hundreds of millions of years. Their rocks carried different histories, different climates, and different living communities shaped in isolation before tectonic motion slowly fused them into one connected world. The scars of those collisions still remain visible, though time has softened them. The Appalachian Mountains of eastern North America and the Scottish Highlands were once part of the same rising chain. When the continents converged, those mountains may have rivaled the modern Himalayas in scale. Since then, rain, ice, rivers, and gravity have worn them down across immense spans of time, reducing towering peaks into rounded ridges and weathered valleys. The coastlines of Pangea were equally unfamiliar. Much of the continental interior flooded seasonally beneath shallow inland seas called epicontinental seas. These waters spread across low-lying plains, leaving behind layers of mud, limestone, and marine fossils far from any permanent ocean margin. In some regions, shorelines advanced and retreated repeatedly over thousands of years, reshaping wetlands, forests, and tidal flats in slow cycles tied to climate and sea level. Beyond the edges of the supercontinent stretched Panthalassa, the enormous superocean surrounding nearly all remaining land. It occupied roughly 70% of Earth's surface on one side of the globe, a planetary ocean so immense that storms could travel uninterrupted for vast distances across open water. Along its margins, volcanic island arcs and deep ocean trenches marked places where seafloor descended back into the mantle. Together, the Tethys and Panthalassa enclosed a world profoundly different from the modern Earth, a planet whose geography operated on scales almost difficult to imagine now, yet whose fragments still survive quietly inside the continents of the present day. In the Permian world, an animal could begin moving across dry land in what is now Eastern Europe and continue southward for thousands of uninterrupted miles, crossing river valleys, fern plains, and volcanic uplands before eventually reaching the regions that would one day become Antarctica. No ocean blocked the path. No narrow strait divided ecosystems into isolated biological islands. The continents were joined into one continuous surface, and life spread across it accordingly. The dominant land animals of this age were not dinosaurs. Those creatures had not yet risen to prominence. Pangea, instead, belonged largely to synapsids, a broad and ancient lineage whose distant descendants would eventually include mammals. Some moved low to the ground on sprawling limbs, while others carried more upright postures, hinting faintly at later evolutionary directions still far beyond the horizon. Among the most widespread were the Dicenodonts, herbivorous synapsids equipped with beaked mouths and compact bodies built for consuming tough vegetation. Some remained small and burrowing, while others grew to the size of modern cattle, grazing across floodplains and semi arid woodlands. Their fossils appear across enormous portions of the former supercontinent, preserved in rocks now separated by entire oceans. One species in particular became quietly famous millions of years after its extinction. Lystrosaurus, roughly pig sized and broad snouted, survived environmental conditions that eliminated countless other lineages. Its fossils have been discovered in southern Africa, India, Antarctica, and other regions once joined within Gondwana. The distribution is so extensive and so precise that it became one of the strongest pieces of biological evidence, suggesting the continents had once been physically connected. Predators moved through this same world in equally distinctive forms. Gorgonopsids occupied the apex positions of late Permian ecosystems, some reaching nearly 3 meters in length. Their elongated skulls carried saber shaped canine teeth, and their bodies combined reptile like and mammal like traits into unfamiliar silhouettes unlike anything alive today. They hunted among conifer forests, seasonal wetlands, and broad inland basins that stretched across the interior of the supercontinent. Because terrestrial environments remained connected across vast distances, evolution operated differently than it does on the fragmented Earth of the present. Isolated gene pools were far rarer. Species spread widely, often occupying enormous geographic ranges before barriers could divide them into separate populations. Distinct regional faunas still existed, shaped by climate and terrain, but the level of planetary biological continuity was unlike anything seen in later geological ages. The evidence persists not only in large animals, but in quieter details preserved inside stone. Fossils of freshwater organisms have been found on opposite sides of the modern Atlantic Ocean, including species incapable of surviving in saltwater. Rivers that now empty into different oceans were once connected systems flowing across unified terrain. Ancient freshwater ecosystems stretch through landscapes that no longer exist in their original form. Plant life recorded the same pattern. Glossopteris, a seed fern adapted to cool southern climates, spread across South America, Africa, India, Australia, and Antarctica. Its leaves later became trapped within coal forming sediments buried beneath multiple continents. Long before plate tectonics was understood, these matching fossil plants hinted that the southern lands had once shared a common geography. Even disease traveled differently in such a connected world. Pathogens encountered few natural barriers capable of halting their spread. Ecosystems rose and declined together across continental scales, linked by migration routes extending farther than any modern terrestrial animal corridor. Life moved through Pangea as though the planet itself possessed a single vast biological bloodstream. Far from the coastlines of Pangea, there were places where rain almost never arrived. Vast stretches of the continental interior sat so distant from open water that moisture could not easily penetrate inland. Across these regions, the air baked under long summers, then cooled sharply during winter darkness. Temperatures may have shifted from negative 30 degrees Celsius in colder seasons to nearly 60 degrees Celsius during peak summer heat, all within the same landscape over the course of a year. No modern continent experiences climatic contrasts on that scale. Pangea altered the atmosphere simply through its size. The arrangement of land and ocean reshaped wind circulation, humidity, and heat transfer across the entire planet. Coastal margins remained comparatively wet, exposed to storms sweeping in from surrounding seas, while the deep interior drifted toward aridity so severe that large regions became difficult for dense life to inhabit consistently. The atmosphere itself carried far more carbon dioxide than today, perhaps 4 to 8 times modern levels during portions of the supercontinent's existence. Global temperatures remained elevated for immense spans of time, and permanent polar ice was absent across much of the period. Even high latitude regions supported forests in some eras, while broad lowland basins accumulated thick sediments beneath heavy seasonal rainfall. Yet the climate was not simply hot. It pulsed rhythmically through colossal monsoon systems, unlike anything now operating on Earth. During seasonal heating, the immense landmass warmed faster than the surrounding oceans, drawing moist air inward from coastal margins. Months later, circulation reversed as temperatures shifted again. These atmospheric oscillations became so powerful that rainfall belts migrated across thousands of miles. Evidence of these ancient wind systems survives quietly inside stone. Across parts of the modern American Southwest, layers of sandstone preserve the fossilized geometry of dunes shaped by prevailing winds from the Pangean interior. The angles and orientations of these ancient sands still record the direction of atmospheric circulation from hundreds of millions of years ago, like weather patterns frozen into rock. The Tethys Sea played a particularly important role within this planetary climate engine. Its shallow tropical waters absorbed enormous quantities of solar heat and released vast amounts of moisture through evaporation. Warm, humid air drifted outward from the sea and fed seasonal rainfall far across neighboring regions. Coastal floodplains surrounding the Tethys likely supported dense vegetation and extensive wetland systems nourished by these recurring monsoon cycles. Older traces of a different world also persisted beneath the supercontinent. Before Pangea fully assembled, extensive equatorial forests had covered large portions of the planet during the Carboniferous period. Those forests later became buried beneath sediments and compressed into coal seams that now lie beneath Europe and North America. Entire ancient ecosystems vanished underground and slowly transformed into concentrated carbon stores, preserving the memory of humid landscapes that no longer existed in the same form once the supercontinent matured. Meanwhile, conditions beneath the oceans grew increasingly unstable because circulation between polar regions remained limited. Deeper marine waters received less oxygen renewal from surface currents. Large portions of the deep ocean became poorly oxygenated, especially during warmer intervals when stratified water layers resisted mixing. Marine ecosystems near the seafloor adapted to increasingly difficult conditions beneath the surface calm. Across Pangea, climate became an expression of geography at planetary scale, shaped not by isolated weather systems, but by the physical arrangement of the world itself, a single landmass large enough to reorganize the atmosphere, oceans, and seasons around its presence. There are layers of rock where life seems to fade almost all at once. Coral reefs disappear, forest ecosystems collapse, entire groups of marine creatures vanish from the fossil record with startling abruptness. Across the boundary between the Permian and Triassic periods, the Earth preserves evidence of a biological crisis so severe that later extinctions appear comparatively restrained beside it. Around 252 million years ago, the planet entered what geologists now call the Permian Triassic extinction event, often known more simply as the Great Dying. Approximately 96% of marine species disappeared. On land, roughly 70% of vertebrate species vanished as ecosystems unraveled across the supercontinent. No other known extinction in Earth's history eliminated so much complex life so completely. The origin of the catastrophe lay far to the north, in the region now occupied by Siberia. There, enormous volcanic eruptions began pouring lava across the landscape in repeated pulses lasting roughly 1 to 2 million years. These eruptions formed the Siberian Traps, one of the largest volcanic provinces ever created on Earth. The total volume of erupted rock was immense enough to bury the contiguous United States beneath lava several miles deep. Yet the greatest damage came not from the lava itself, but from what the eruptions released into the atmosphere. Vast quantities of carbon dioxide and methane accumulated in the air over geologically brief timescales, driving rapid global warming estimated at roughly 10 to 15 degrees Celsius. Oceans warmed alongside the atmosphere, altering chemistry that marine ecosystems had depended upon for millions of years. As temperatures rose, seawater retained less dissolved oxygen. Large portions of the deep ocean became increasingly stagnant and depleted. Acidification spread through marine environments as excess carbon dioxide dissolved into seawater. Some evidence also suggests severe disruption of the ozone layer, exposing surface ecosystems to elevated ultraviolet radiation. Multiple environmental stresses unfolded simultaneously, reinforcing one another across land and sea. The terrestrial world deteriorated in parallel. Forest systems collapsed across wide regions of Pangea, interrupting the formation of peat swamps that normally accumulated into coal deposits over time. Geologists refer to the aftermath as the coal gap, an interval in which coal-forming ecosystems became extraordinarily rare because global vegetation had been devastated so extensively. Amid that collapse, a few hardy survivors expanded into the emptied world. Lystrosaurus endured where many other synapsids failed. Its compact body, broad chest, and likely burrowing behavior may have allowed it to tolerate harsh environmental conditions better than larger or more specialized animals. Across portions of the early Triassic fossil record, the remains of Lystrosaurus dominate entire assemblages, comprising as much as 95% of some vertebrate fossil beds. The ecological diversity that had once spread across Pangea narrowed dramatically, complex food webs simplified. Many surviving landscapes supported only sparse communities of generalist species capable of enduring unstable climates and poor environmental conditions. Recovery unfolded slowly across millions of years as ecosystems cautiously rebuilt themselves from a diminished biological foundation. By the time life began diversifying again, the supercontinent itself had already entered a quieter transformation beneath the surface. Deep within the crust and mantle, the tectonic forces that once assembled Pangea continued shifting gradually onward, carrying the surviving lineages of Earth into a changing planetary geography shaped by extinction, survival, and slow continental motion. At first, the separation was almost invisible. No single moment announced the beginning of the breakup. Forests still covered wide plains. Rivers continued crossing connected terrain. Animals migrated across land that remained physically joined. Yet deep beneath the crust, forces moving through the mantle had begun pulling sections of the supercontinent in opposing directions, slowly placing the surface under tension. Rock does not respond to stress all at once. Continental crust bends gradually over immense spans of time. As stretching continued, the lithosphere thinned and weakened, allowing long fractures to spread across the interior of Pangea. This process is known as rifting, the slow tearing apart of a continent from within. Instead of mountains rising through compression, the ground began subsiding downward into elongated basins where the crust was being pulled apart. The earliest major stages of this rifting began roughly between 230 and 200 million years ago during the Triassic period. The fracture zone extended through regions that are now the eastern United States, northwestern Africa, and parts of what would later become the Atlantic margins. These lands, currently separated by thousands of kilometers of ocean, once sat directly beside one another along the same developing rupture. On the surface, a rift valley forms as stretched crust collapses between parallel fault systems. The landscape sinks into long troughs bordered by elevated ridges and fractured escarpments. Earthquakes become frequent as blocks of crust shift unevenly under strain. Volcanoes begin appearing along the rift axis where magma rises more easily through the thinning lithosphere. Lakes often accumulate within the depressions, collecting sediment and preserving detailed records of the changing environment. A modern example survives today in East Africa. From Ethiopia southward through Kenya and Tanzania, the African continent is presently undergoing active rifting. Valleys continue widening gradually, while volcanic systems remain active along the fracture zone. In tens of millions of years, if the process continues uninterrupted, seawater may eventually flood the region and create a new ocean basin separating eastern Africa from the rest of the continent. During the breakup of Pangea, volcanic activity intensified dramatically along the developing rift system. Around 201 million years ago, enormous eruptions produced the Central Atlantic Magmatic Province, often abbreviated as CAMP. Lava flooded across vast portions of the supercontinent in one of the largest volcanic events associated with continental rifting. The eruptions likely contributed to severe environmental instability near the end of the Triassic period, placing additional stress on ecosystems already adapting to a changing world. Fragments of these lava flows still survive today across several continents now divided by the Atlantic Ocean. Matching volcanic rocks appear in northeastern Brazil, West Africa, eastern North America, and parts of Iberia. They were once part of the same eruptive system before continental separation carried them apart over millions of years. As rifting progressed, The crust eventually became thin enough for seawater to enter the developing basins. Narrow marine channels spread into low regions between the separating landmasses. At first, these waters resembled shallow inland seas, restricted and irregular. Gradually, continued spreading widened the gap further, allowing more persistent oceanic circulation to develop. The earliest Proto-Atlantic was still modest in scale, perhaps comparable at first to the modern Red Sea, a narrow ribbon of water lying within a continental fracture. But beneath that young seaway, new oceanic crust had already begun forming, marking the quiet birth of an ocean that would continue expanding for hundreds of millions of years. The Atlantic Ocean feels ancient when viewed from a modern shoreline. Its tides shape entire continents, its storms cross thousands of kilometers of open water, and its currents regulate climates across half the planet. Yet, in geological terms, the Atlantic is surprisingly young. There was a time when no ocean existed at all between the Americas and Africa, only a widening fracture, slowly admitting seawater into the center of a separating world. The ocean did not appear all at once. Its formation unfolded gradually across different regions over tens of millions of years. The Central Atlantic began opening around 180 million years ago. Farther north, separation progressed later, with the North Atlantic developing roughly 140 million years ago. The South Atlantic followed afterward, opening primarily between 130 and 100 million years ago as South America and Africa finally drifted apart. Beneath this process lay a mechanism operating continuously along the floor of the growing basin. As continental crust separated, pressure decreased within the mantle below the rift zone, allowing molten rock to rise upward. This magma cooled and solidified into fresh oceanic crust along the center of the widening ocean. The process, known as seafloor spreading, transformed the original continental fracture into a permanent ocean basin with newly created crust forming continuously at its center. The Mid-Atlantic Ridge marks this boundary today. Extending roughly 40,000 kilometers from north to south beneath the ocean's surface, it forms the longest mountain range on Earth. Most of it remains hidden underwater, running quietly through the middle of the Atlantic basin. Along its crest, volcanic activity and tectonic motion continue shaping new seafloor at rates measurable even within a human lifetime. In a few places, the ridge rises above sea level. Iceland sits directly atop this spreading center, positioned where magma from the mantle reaches the surface in extraordinary abundance. Lava fields, volcanic plateaus, and geothermal systems there reveal a small exposed section of the process usually concealed beneath deep water. The ocean floor itself preserves a remarkably precise timeline of the Atlantic's expansion. Near the ridge axis, the crust remains youngest, recently formed from cooled magma. Moving outward toward the continental margins, the rocks grow progressively older. The symmetry on either side of the ridge records the gradual widening of the ocean basin, almost like growth rings spreading outward from a central seam. During its earliest stages, the Atlantic was not yet the broad, well-circulated ocean known today. Restricted connections and intense evaporation likely made portions of the young basin warmer and saltier than modern seawater. Shallow marine environments developed along the margins, while sediments accumulated within subsiding basins between the drifting continents. The separation between South America and Africa remains one of the clearest examples of continental rifting preserved in the geological record. Rock formations, sedimentary basins, and fault systems in Brazil align closely with corresponding structures in West Africa, including the Benue Trough and the Niger Delta region of modern Nigeria. The pieces still fit together despite the ocean now lying between them. As the distance widened, biological exchange between the continents finally ended. Populations once connected across shared terrain became isolated on opposite sides of the growing ocean. Over millions of years, separate evolutionary histories emerged from those divisions. South American lineages diverged from African relatives, eventually producing entirely distinct communities of predators, birds, reptiles, and forests, shaped by isolation within different continental worlds. While northern continents were already separating around the young Atlantic, the southern supercontinent followed a slower and more uneven path. Gondwana did not fracture through one dramatic rupture. Its land masses drifted apart gradually across immense spans of time, each carrying fragments of ancient ecosystems into increasing isolation. For much of Pangea's existence, Gondwana had retained a distinct geological identity from Laurasia to the north. Its southern position exposed it to different climates, glacial histories, and environmental pressures long before the final breakup accelerated. When separation deepened, the southern continents moved along trajectories unlike those unfolding elsewhere on Earth. India's journey became one of the most extraordinary episodes in tectonic history. Around 130 million years ago, the Indian plate detached from Antarctica and Africa before beginning a rapid movement northward across the Tethys Ocean. At its peak, India may have traveled between 15 and 20 centimeters per year, roughly twice the speed of most tectonic plates. The reasons for that unusual velocity remain debated, though mantle dynamics beneath the plate likely played a major role. As India moved north, Madagascar separated from it roughly 88 million years ago. Isolation transformed the island into a biological refuge unlike any neighboring landmass. Species trapped there evolved independently for millions of years, eventually producing lemurs, fossas, and thousands of endemic organisms found nowhere else. Entire evolutionary lineages survived because the island drifted beyond the reach of surrounding continents. Farther south, Antarctica experienced an even greater transformation. Earlier in its history, the continent had not been frozen beneath permanent ice. Forests once spread across broad valleys, and rivers crossed temperate landscapes, supporting diverse plant communities. Coal seams preserved beneath Antarctic rock still contain fossil remains from those vanished forests, evidence of climates now almost impossible to associate with the modern continent. The transition toward glaciation began when Australia separated from Antarctica around 45 million years ago. Later, between roughly 34 and 30 million years ago, the Drake Passage opened between Antarctica and South America. For the first time, ocean water could circulate continuously around the southern continent without interruption from connected land. That circulation formed the Antarctic Circumpolar Current, now the most powerful ocean current on Earth. Flowing endlessly around Antarctica, it prevented warmer waters from lower latitudes from reaching the continent. Thermal isolation followed gradually. Temperatures declined. Ice sheets expanded outward across the landmass until glaciers buried nearly the entire continent beneath thick accumulations of ice. The freezing of Antarctica altered global climate systems far beyond the polar region itself. Ocean circulation patterns shifted, atmospheric behavior changed, and Earth entered a cooler climatic phase that continues influencing the modern world. A continent once covered in forests became a frozen desert through the geometry of drifting continents and changing seaways alone. Australia, meanwhile, continued moving northward in prolonged isolation. When it separated from Antarctica, it carried with it a fauna dominated by marsupials and monotremes rather than placental mammals. Over millions of years, kangaroos, wombats, koalas, and countless other distinctive lineages diversified across the continent. Australia became almost like a drifting biological archive, preserving ancient evolutionary pathways while ecosystems elsewhere followed different directions. Across Gondwana, separation unfolded slowly enough that each fragment developed its own climate, circulation patterns, and ecological identity. What had once been a connected southern world gradually transformed into isolated continental realms shaped by distance, water, and time. The first dinosaurs emerged, while the continents still remained largely connected. Their footprints crossed landscapes that stretched across much of the planet without major ocean barriers interrupting migration. In rocks from the Triassic period, closely related dinosaur species appear across regions now separated by immense distances, from South America to Africa to North America. The world was still unified enough for animal populations to spread widely across connected terrain. As the supercontinent continued separating, that continuity slowly disappeared. Rift valleys widened into seas, coastlines drifted farther apart, and populations that once mixed freely became isolated from one another. Evolution began operating within separated continental worlds. Over millions of years, dinosaurs on different landmasses followed increasingly distinct evolutionary paths shaped by local climates, vegetation, prey, and competition. The Jurassic period became an age of enormous diversification. Sauropods, the long-necked herbivores that included Brachiosaurus and Diplodocus, expanded into many ecological forms, while fragments of Pangea still retained occasional land connections. Some species roamed broad floodplains and fern-rich valleys in enormous herds, feeding on vegetation beyond the reach of smaller herbivores. Their immense size may have helped them process low nutrient plant matter efficiently across environments where seasonal conditions fluctuated dramatically. At the same time, geographic separation encouraged the emergence of different predator lineages on opposite continents. Across Gondwanan regions such as South America, India, and Africa, the abelisaurids became dominant hunters. These theropods often possessed short skulls, reduced forelimbs, and deep muscular jaws adapted for powerful bites. Meanwhile, northern continents followed a different trajectory. In Laurasia, tyrannosaur ancestors gradually evolved into large-bodied apex predators, occupying ecological roles parallel to those of the southern hunters. These lineages developed independently for millions of years, separated by expanding oceans and shifting coastlines. The fragmentation of continents transformed geography into an evolutionary filter, dividing once connected animal populations into isolated biological experiments unfolding simultaneously across different parts of the planet. In North Africa, Spinosaurus evolved within coastal wetlands, shaped by the broadening tethys margins. Its elongated jaws, dense limb bones, and fish-eating adaptations reflected an environment dominated by river systems, estuaries, and shallow aquatic habitats. Local geography influenced anatomy directly. As seaways expanded and climates shifted, ecosystems became increasingly regional rather than global. Plant evolution changed alongside the dinosaurs. Around 130 million years ago, flowering plants began spreading across the fragmented continents. Angiosperms transformed terrestrial ecosystems by altering food sources, forest structure, and insect behavior. Pollinating insects diversified alongside them, often evolving separately on isolated landmasses. Forests in different regions gradually developed distinct floral compositions shaped by continental isolation and climate. One of the clearest records of this isolated evolution survives in the Morrison Formation of North America. Deposited during the late Jurassic, it preserves river systems, floodplains, and dinosaur communities unlike those known elsewhere. Massive sauropods, predatory theropods, crocodilians, insects, and plants occupied ecosystems shaped by millions of years of relative separation from southern continental faunas. By the late Cretaceous period, the planet had become a patchwork of biological kingdoms. Different continents supported entirely different dinosaur communities, each molded by its own geography and evolutionary history. The breakup of Pangea had not reduced life's diversity, it had multiplied it, transforming one connected world into many isolated evolutionary theaters, unfolding side by side across the drifting Earth. As the continents drifted farther apart, the oceans did not simply widen outward into empty space. The changing shape of the sea floor altered sea levels across the entire planet. Regions that had once been dry land slowly disappeared beneath shallow inland waters, transforming continental interiors into warm marine environments, unlike anything visible on modern maps. This flooding began because newly formed oceanic crust behaves differently from older seafloor. Fresh crust rising along spreading ridges remains hot and relatively buoyant, occupying more physical volume beneath the oceans. During the Cretaceous period, seafloor spreading accelerated across several ocean basins at once. The elevated ocean floor displaced enormous quantities of seawater upward onto the continents, causing global sea levels to rise dramatically. One of the clearest examples appeared in North America around 85 million years ago. A broad inland sea, known as the Western Interior Seaway, extended from the Gulf of Mexico northward toward the Arctic Ocean, dividing the continent into eastern and western landmasses. At its greatest extent, the seaway reached roughly 1,000 kilometers in width and nearly 800 meters in depth, though much of it remained relatively shallow compared to modern oceans. Its waters were warm, rich in nutrients, and crowded with marine life. Mosasaurs hunted through the seaway as dominant marine predators, while plesiosaurs moved through deeper channels with long necks, trailing behind streamlined bodies. Ammonites drifted through the water column in immense numbers, their coiled shells accumulating across the seafloor after death. Sharks, giant fish, turtles, and countless microscopic organisms filled the ecosystem beneath the surface. The sediments deposited in these shallow seas still shape modern landscapes. The white cliffs of Dover in England and the chalk plains of Kansas formed from compressed remains of microscopic marine organisms that settled continuously onto ancient seafloors. Over millions of years, their calcium-rich skeletons accumulated into thick chalk deposits now exposed far above sea level after later uplift and erosion. Europe during this period looked entirely different from the connected continent known today. Much of it existed as a fragmented archipelago of tropical islands surrounded by shallow marine channels. Coastlines shifted repeatedly as sea levels fluctuated, producing isolated habitats where plants and animals evolved under changing environmental conditions. These inland seas became some of the most biologically productive ecosystems in Earth's history. Warm temperatures, shallow sunlight penetration, and abundant nutrients supported enormous quantities of plankton and marine life. Organic material accumulated within oxygen, poor sediments along basin floors, eventually becoming major petroleum source rocks. Many oil reserves beneath North America and the Middle East originated within these ancient, shallow marine systems. The flooded continents did not remain submerged permanently. As seafloor spreading slowed later in geological time, the young oceanic crust gradually cooled and became denser. Ocean basins deepened as the seafloor subsided, lowering global sea levels and exposing previously submerged land once more. Inland seas retreated slowly toward the oceans, leaving behind layers of marine sediment across continental interiors. In North America, the draining of the western interior seaway reconnected eastern and western ecosystems that had evolved separately for millions of years. Animal populations spread across the reunited landmass, mixing lineages that had once been divided by water. The geography of the continents shifted again, and life shifted with it, responding continuously to the changing shape of the earth beneath. 66 million years ago, a mountain sized asteroid entered Earth's atmosphere above a planet already divided into separate continents, isolated ecosystems, and widening oceans. The object struck near the present day Yucatan Peninsula with a force far beyond any volcanic eruption or earthquake in recorded human experience. In moments, the impact excavated a crater more than 180 kilometers wide and released enough energy to alter conditions across the entire globe. The impact site, now buried beneath younger sediments, is known as Chicxulub. Around the world, geologists later discovered a thin layer within rock strata containing unusually high concentrations of iridium, an element rare in Earth's crust but common in asteroids. That layer appears on continents separated by oceans, preserved in marine sediments and terrestrial rocks alike, recording the moment when debris from the impact spread through the atmosphere worldwide. The collision ignited fires across enormous regions as molten ejecta re entered the atmosphere and heated the sky itself. Dust, sulfur compounds, and soot accumulated high above the planet, blocking sunlight for extended periods. Temperatures fell sharply. Photosynthesis weakened across both land and ocean ecosystems. Food chains dependent upon plant productivity began collapsing from the bottom upward. Yet the geography of the late Cretaceous Earth shaped how the catastrophe unfolded. Had a connected supercontinent still existed, some distant interior refuges might have remained comparatively insulated from the worst disruptions. Instead, isolated continents experienced different environmental stresses depending on ocean circulation, climate, and local ecosystems. The extinction was global, but its effects unfolded unevenly across the fragmented world. Non-avian dinosaurs disappeared entirely. Marine reptiles vanished alongside them, and many plant groups suffered severe losses. But survival patterns varied between regions. Some freshwater systems endured better than coastal ecosystems. Certain southern landmasses recovered differently than northern continents, with broader connected habitats and more intense climatic instability. Small mammals proved unusually resilient during the crisis. Their limited food requirements, burrowing behavior, and flexible diets allowed some species to survive environmental collapse more effectively than large specialized animals. The fragmented arrangement of the continents also meant mammals had already diversified into many isolated lineages before the impact occurred. Extinction in one region did not necessarily eliminate related groups elsewhere. Marsupials survived within South America and later expanded through Antarctica into Australia, while those southern continents still retained partial connections. Their continued existence depended entirely on the specific arrangement of drifting land masses during that interval of geological history. Continental geography shaped survival routes as profoundly as biology itself. At the same time, Earth was already under stress before the asteroid arrived. Across the Indian plate, massive volcanic eruptions, known as the Deccan Traps, had been releasing gases and lava over prolonged intervals. India's rapid northward drift may have contributed to the unusual mantle activity beneath the region. Atmospheric chemistry and climate were likely already fluctuating before the impact darkened the skies further. Recovery unfolded gradually across millions of years. Forests returned unevenly. Marine ecosystems rebuilt themselves from surviving lineages. In some isolated southern environments, ecological recovery may have progressed more steadily than within heavily disrupted northern systems. The age of dinosaurs ended not in one instant, but through a prolonged collapse followed by slow biological renewal. When ecosystems stabilized again, mammals inherited a world already divided by oceans and drifting continents. Their diversification unfolded across separated landmasses that encouraged independent evolutionary paths. The fragmented geography left behind by Pangea ensured that the mammalian age would become as regionally diverse and biologically varied as the dinosaur world that had disappeared before it. After the extinction that ended the age of dinosaurs, the continents remained divided by widening oceans and isolated seas. Mammals inherited a planet already fragmented into separate evolutionary worlds. What followed was not a slow replacement of one dominant group by another, but an extraordinary diversification unfolding across disconnected landmasses that no longer shared the same biological history. During the Paleocene and Eocene epochs, between roughly 66 and 34 million years ago, mammals expanded into ecological roles that had once belonged to dinosaurs. Small insect eaters evolved into predators, grazers, climbers, swimmers, and burrowers. Forests, coastlines, floodplains, and mountain valleys filled with increasingly specialized forms as ecosystems recovered from the earlier extinction. Some continental connections still lingered during the early Paleocene. North America and Europe remained intermittently linked through Greenland, allowing limited exchanges of mammal species between the two regions before that northern route disappeared beneath colder seas. These temporary corridors allowed related groups to spread across both continents before isolation resumed once more. Elsewhere, complete separation produced stranger outcomes. South America became an island continent for nearly 30 million years, cut off from the mammalian faunas evolving elsewhere. Within that isolation, entirely unique animal groups emerged. Giant ground sloths moved slowly through forests and open habitats. Glyptodonts, armored relatives of armadillos, reached sizes comparable to small cars. Native hoofed mammals evolved independently from horses or deer, filling grazing niches through separate evolutionary pathways found nowhere else on Earth. Africa followed its own isolated trajectory as well. For much of the Paleocene and Eocene, the continent remained surrounded by water, separated from Eurasia by the shrinking Tethys Sea. Within that long isolation, several unusual mammal groups evolved from shared ancestors unique to Africa. Elephants, hyraxes, aardvarks, and tenrecs all trace their origins to this isolated evolutionary history. Their outward appearances later became dramatically different, yet their ancestry remained unexpectedly connected beneath the surface. As Africa drifted northward and India approached Asia, the Tethys Sea gradually narrowed. Coastlines shifted, shallow marine basins closed, and future mountain systems slowly began forming along zones of collision. The eventual closure of the Tethys would help create both the Alps and the Himalayas, reshaping atmospheric circulation and ocean currents across much of the planet. Along the shores of that shrinking sea, another transformation unfolded. Early whales evolved from terrestrial mammals in what is now Pakistan, then positioned along warm coastal environments bordering the Tethys. Over time, these animals adapted increasingly to aquatic life. Limbs became flippers, tails strengthened for swimming, and bodies reshaped themselves for movement through water. As Eocene oceans remained warm, whales spread outward through marine corridors, connecting distant regions of the fragmented world. Europe later experienced a major ecological turnover known as the Grande Coupure around 34 million years ago. As connections formed between Europe and Asia, Asian mammals spread westward into ecosystems long isolated from outside competition. Many endemic European lineages disappeared while new immigrant species established themselves across the continent. Australia remained the most isolated mammalian world of all. After separating from Antarctica, it carried primarily marsupials and monotremes into prolonged isolation without placental mammals dominating its ecosystems. Over immense spans of time, that separation produced the most distinctive mammal fauna on Earth, shaped almost entirely by isolation, geography, and the drifting inheritance of Gondwana itself. Far above sea level, near the summit of Everest, there are fragments of ancient marine organisms locked inside limestone. Tiny shells and seafloor sediments now rest among snow and exposed rock at the highest elevation on Earth. Long before those peaks existed, the region lay beneath the warm waters of the Tethys Ocean, part of a marine world separating drifting continents. India began its northward journey roughly 130 million years ago after separating from Gondwana. Once detached, the Indian plate moved rapidly across open ocean toward Eurasia, traveling nearly 6,000 kilometers over tens of millions of years. Compared with most tectonic plates, India moved with unusual speed, advancing steadily through the shrinking Tethys Basin, while oceanic crust disappeared beneath Eurasia ahead of it. The first stages of collision likely began around 50 to 55 million years ago, though geologists still debate the precise timing. Unlike collisions involving dense oceanic crust, this encounter occurred between two buoyant continental plates. Neither continent could sink easily into the mantle beneath the other. Instead, the crust compressed, folded, thickened, and rose upward under immense pressure. The Himalayas formed from that compression. Layers of crust that had once rested near sea level were pushed progressively higher as India continued forcing itself beneath southern Asia. The mountains are geologically young despite their enormous size. Everest itself did not exist 50 million years ago. Its slopes, glaciers, and exposed ridges emerged gradually through uplift occurring long after the collision began. The process has not ended. India continues drifting northward today, and the Himalayas are still rising as a result. Everest currently reaches approximately 8,849 meters above sea level, with uplift continuing at a rate of several millimeters each year. Earthquakes across the Himalayan region reveal that the crust remains under constant tectonic stress as the collision continues deep below the surface. The same forces that elevated the mountains also created the Tibetan Plateau. Averaging more than 4,500 meters in elevation, it became the largest and highest plateau on Earth. Sometimes described as the roof of the world, the plateau altered atmospheric circulation across much of Asia by introducing an immense elevated landmass into global climate systems. That uplift helped shape the Indian monsoon. During summer months, the plateau heats strongly beneath sunlight, influencing pressure systems across southern Asia. Moist air from the Indian Ocean is drawn northward toward the elevated interior, producing seasonal rainfall patterns that now sustain rivers, forests, farmland, and human populations across enormous regions of the continent. Evidence of the vanished Tethys Ocean still survives throughout the Himalayas. Marine fossils embedded within limestone layers near Everest preserve traces of organisms that once lived beneath shallow tropical seas. Rocks now standing among glaciers originally formed underwater, deposited gradually on ancient seafloors before tectonic compression carried them upward through the crust. The collision between India and Eurasia also closed most remaining portions of the Tethys itself. The broad marine corridor that once separated continents narrowed steadily as land advanced northward. Today, the Mediterranean Sea remains the last major remnant of that vanished oceanic system. Even that surviving fragment is temporary. Africa continues drifting slowly north toward Europe, compressing the Mediterranean basin in the same gradual manner that once closed the Tethys. The forces that built the Himalayas remain active across the planet, continuing the long geological rearrangement that began when Pangea first started to separate. Mountain ranges often appear permanent when viewed from valleys below them. Their ridges seem fixed against the horizon, older than weather, older than forests, older than memory itself. Yet every major mountain chain on Earth is the visible surface of ancient motion, the slow upward expression of continents colliding, subducting, folding, and drifting across the planet over immense spans of time. The Himalayas are only one chapter in that larger geological story. Across nearly every continent, the breakup and rearrangement of Pangea generated mountain systems through entirely different mechanisms, each preserving a separate record of tectonic movement beneath the crust. The Alps began forming around 35 million years ago as Africa drifted steadily northward into Europe. Between the approaching continents lay remnants of the shrinking Tethys Sea. As the collision intensified, marine sediments that had accumulated across the ancient seafloor compressed, folded, and rose upward into mountain peaks. Many upper alpine layers still contain fossil marine organisms embedded within limestone and sedimentary rock. Entire sections of the mountains were once underwater, resting quietly beneath a vanished sea. Farther west, the Rockies formed through a different process altogether. Rather than a direct continental collision, they emerged from shallow angle subduction beneath western North America during an event known as the Laramide orogeny, beginning around 80 million years ago. Oceanic crust from the Pacific region descended beneath the continent at an unusually low angle, transmitting compressional forces deep into the interior of North America. The crust responded by thickening and uplifting far inland from the coastline itself. Along the western edge of South America, another mountain system continued rising almost continuously for tens of millions of years. The Andes formed through the subduction of the Nazca Plate beneath the South American continent after South America drifted westward away from Africa. Stretching roughly 7,000 kilometers, they became the longest continental mountain range on Earth. Volcanic activity, earthquakes, and crustal uplift still shape the Andes today, reflecting an active collision zone beneath the western margin of the continent. Not all mountain ranges remain sharp and elevated forever. The Ural Mountains formed approximately 300 million years ago during collisions that helped assemble Pangea itself. They once rose far higher than they do today, but hundreds of millions of years of erosion gradually reduced them into lower ridges and rolling terrain. Even so, they still mark the ancient suture line where continental masses merged long before the supercontinent later fragmented apart again. The Sierra Nevada of western North America developed through repeated granite intrusions associated with subduction along the continent's Pacific margin during the Cretaceous period. Molten material rising deep within the crust cooled slowly underground, later becoming exposed through uplift and erosion. Their granite cliffs preserve a quieter but equally powerful record of tectonic activity tied to shifting continental boundaries. These mountain systems reshaped climate as profoundly as geography. Rising ranges redirect atmospheric circulation and alter rainfall patterns across entire continents. The Andes blocked moist Pacific air, contributing to formation of the Atacama Desert, one of the driest nonpolar regions on Earth. The Rockies influenced the development of the Great Plains through large-scale rain shadow effects. The Himalayas and Tibetan Plateau helped create the Gobi and Taklamakan deserts across Central Asia by preventing moisture from reaching the continental interior. Deserts and mountains therefore share the same geological ancestry. Every major arid region on Earth owes part of its existence to uplifted terrain, and those mountains themselves exist because continents continued moving long after Pangea began to break apart. The oceans of the modern world move with remarkable precision. Warm water travels northward through narrow corridors. Cold currents circle the poles, and deep water sinks slowly into abyssal basins before resurfacing thousands of kilometers away. None of these circulation patterns could have existed while Pangea remained whole. The breakup of the supercontinent did not merely rearrange coastlines, it reorganized the movement of heat across the entire planet. When Pangea still dominated Earth's surface, global ocean circulation centered around Panthalassa, the immense superocean surrounding the supercontinent. With most land concentrated into one connected mass, currents followed pathways fundamentally different from those of the present world. Heat distribution across the oceans operated through broader, less compartmentalized circulation systems, and polar exchange remained comparatively restricted. As the Atlantic Ocean widened, a new north-south marine corridor gradually emerged between separating continents. Over millions of years, this opening allowed the development of a major circulation system now known as the Atlantic Meridional Overturning Circulation, often abbreviated as AMOC. This system includes the Gulf Stream, one of the most influential ocean currents on Earth. The Gulf Stream transports enormous quantities of warm tropical water northward along the eastern margin of North America before curving across the Atlantic toward Europe. That heat transfer strongly moderates temperatures across Western Europe. Cities positioned at relatively high latitudes remain far warmer in winter than other regions at similar distances from the equator. Without the Atlantic corridor created by continental separation, this circulation could not function in its present form. Western Europe would experience a much colder climate, closer to conditions found in Labrador or parts of eastern Canada. Farther south, another tectonic event reshaped global circulation even more dramatically. Around 34 million years ago, South America fully separated from Antarctica, opening the Drake Passage between the two continents. For the first time, ocean water could circulate continuously around Antarctica without interruption from land barriers. That opening allowed formation of the Antarctic Circumpolar Current, the strongest ocean current on Earth. Carrying approximately 130 million cubic meters of water every second, it flows endlessly around the southern continent, isolating Antarctica from warmer ocean waters farther north. Thermal isolation intensified rapidly once the current became established. Temperatures declined across Antarctica, glaciers expanded, and permanent continental ice sheets developed. The consequences extended far beyond the polar region itself. Antarctic glaciation altered atmospheric circulation, sea levels, and planetary climate patterns on a global scale. The Ice Age rhythms of the modern Earth emerged partly because this current transformed Antarctica into a permanently frozen continent. Another major shift occurred much later when North and South America became connected through formation of the Isthmus of Panama roughly 3 to 4 million years ago. Before that connection formed, water flowed relatively freely between the Atlantic and Pacific Oceans through the Central American Seaway. As the seaway closed, exchange between the oceans became restricted, changing salinity and temperature balances across both basins. The Atlantic gradually became saltier, strengthening deep water formation within northern regions and intensifying circulation associated with the Gulf Stream. These changes may have contributed to stronger northern hemisphere glaciation during the late Cenozoic, reinforcing the climatic cycles that shaped landscapes, ecosystems, and eventually the environmental pressures influencing early human evolution. The modern climate system, therefore, emerged not simply from atmosphere or sunlight alone, but from the geography of drifting continents. Ocean currents followed the openings and closures created by tectonic movement, carrying heat through pathways carved slowly by the long separation of Pangea itself. For tens of millions of years, South America drifted in biological solitude. Its forests, plains, and wetlands belonged to animals found nowhere else on Earth. Strange hoofed mammals wandered through subtropical woodlands, armored herbivores browsed beneath giant trees, and enormous flightless predators stalked the open terrain. Far to the north, an entirely separate mammalian world evolved along its own path. Then, approximately 3 million years ago, tectonic movement quietly closed the gap between them. The Isthmus of Panama rose gradually from the sea as volcanic activity and plate collision lifted a narrow bridge of land between North and South America. What had once been open water became a corridor of migration. Two isolated continents, separated for nearly 30 million years, suddenly shared the same ecological stage. The exchange that followed became one of the most important biological events of the Cenozoic era. South American animals began moving northward into unfamiliar territory. Giant ground sloths, including the immense Megatherium, crossed into North America alongside glyptodonts, heavily armored relatives of armadillos with domed shells large enough to rival small cars. Capybaras entered new river systems, opossums spread through expanding forests, and armadillo ancestors slowly advanced across warmer southern landscapes. At the same time, northern species moved southward in even greater numbers. Horses returned to a continent where their distant ancestors had once evolved before disappearing millions of years earlier. Deer entered South American grasslands, while tapirs, peccaries, camels, and predatory cats followed behind them. Among those predators was the ancestor of the modern jaguar, a powerful hunter that adapted quickly to tropical forests and wetlands. The interchange, however, was profoundly uneven. Many North American species proved highly competitive within southern ecosystems. Over the following millions of years, numerous endemic South American mammal groups declined or vanished entirely. Evolutionary isolation had produced extraordinary diversity, but it had also created ecosystems unprepared for the arrival of unfamiliar competitors and predators. Among the most striking casualties were the terror birds, the forest racids. For millions of years, these towering flightless predators had occupied the apex role across much of South America. Some species stood over 3 meters tall, moving through open country on powerful legs while hunting with enormous hooked beaks. A few expanded northward after the land connection formed, briefly entering parts of North America. Yet their dominance faded as invading mammalian carnivores spread southward. The ecological role once held by terror birds gradually shifted to cats and other placental predators. Not every southern lineage disappeared. Some endured and became permanent parts of northern ecosystems. The Virginia opossum remains the only marsupial native to North America today, a surviving witness to that ancient migration. Armadillos also persisted, extending their range steadily northward over immense spans of time. Even now, their movement continues slowly across the southern United States. Plants cross the land bridge as well. Forest species from both continents encountered unfamiliar climates and pollinators, producing new ecological combinations across mountains, wetlands, and tropical corridors. Seeds dispersed into landscapes that had evolved separately for millions of years, and previously isolated plant lineages began intermingling across the connected Americas. The closure of a narrow seaway therefore reshaped two continents at once. A tectonic event lasting millions of years altered migration, competition, extinction, and survival, quietly transforming the biological identity of an entire hemisphere. Long after dinosaurs vanished and the continents settled into shapes beginning to resemble the modern world, the remains of the ancient Tethys Ocean still lingered between Europe and Africa. What is now the Mediterranean Sea survived as a narrowing marine corridor caught between converging plates. Then, approximately 6 million years ago, that corridor closed, and one of the strangest geological events in Earth's recent history quietly began. As the African plate continued drifting northward, tectonic uplift near what is now the Strait of Gibraltar restricted the connection between the Atlantic Ocean and the Mediterranean basin. The sea lost access to its only major source of incoming water. Rivers still flowed inward from Europe and Africa, but under the warm subtropical climate of the region, evaporation greatly exceeded freshwater input. The Mediterranean began shrinking. Over roughly 600,000 years, sea levels inside the basin dropped dramatically. Coastlines retreated farther and farther outward, exposing immense plains of salt and sediment beneath an increasingly hostile sky. Eventually, much of the basin transformed into a chain of hypersaline lakes separated by vast desert depressions. In some regions, the floor of the Mediterranean lay approximately 3 to 5 kilometers below modern sea level. The physical evidence for this vanished landscape still survives beneath the modern seabed. Drilling operations have revealed enormous salt deposits buried beneath younger sediments, some reaching nearly 3 kilometers thick. These layers consist largely of evaporite minerals left behind as seawater repeatedly evaporated under intense heat. What had once been an open sea became, over immense spans of time, a geological basin slowly crystallizing into salt. The rivers surrounding the region responded dramatically to the falling water level. As the basin deepened, rivers descending toward it carved downward with extraordinary force. The Nile cut a canyon far deeper than the modern Grand Canyon, slicing through bedrock as it chased the retreating shoreline. Similar canyons formed beneath rivers flowing from southern Europe. Today, these ancient gorges remain hidden beneath younger sediment and seawater, preserved as buried records of a vanished world. At its driest stage, the Mediterranean basin may have resembled an immense sunken desert bordered by towering cliffs. Dense salt flats stretched across portions of the exposed floor, while isolated lakes shimmered beneath heavy, mineral-rich air. Yet this condition was temporary. Tectonic movement continued reshaping the region, and eventually the barrier at Gibraltar weakened. Approximately 5.33 million years ago, Atlantic water broke through once again. The event that followed is known as the Zanclean Flood. Water from the Atlantic surged into the desiccated basin through a rapidly widening channel at Gibraltar. Some geological models suggest the refilling happened astonishingly quickly, perhaps over only a few thousand to tens of thousands of years. The incoming torrent may have formed waterfalls hundreds of meters high, releasing more water each day than all modern rivers combined. As the basin filled, marine ecosystems gradually returned. Species recolonized the recovering sea, though many organisms that survived the crisis remained isolated long enough to evolve into unique endemic forms. The Mediterranean world that emerged afterward carried the memory of that interruption within its biology, chemistry, and geology. Even now, beneath the calm blue surface of the modern Mediterranean, enormous layers of buried salt remain sealed below the seafloor, quiet evidence that an entire sea once disappeared from the earth. The coldest chapters of recent Earth history began not with snow, but with continental movement. Long before glaciers advanced across the northern hemisphere, the fragments of Pangea had already been repositioning oceans, redirecting winds, and carrying entire landmasses toward new latitudes. By the time the modern Ice Age rhythm emerged, the planet's geography had become fundamentally different from the world of the supercontinent. An intact Pangea could not have produced the same glacial system that exists today. Large permanent ice sheets require land positioned near the poles, where snow can accumulate year after year without completely melting. During much of Pangea's existence, continental arrangements and ocean circulation prevented that kind of stable polar freezing. Only after Gondwana fragmented and Antarctica drifted into isolation over the South Pole did the conditions for long-term glaciation fully emerge. Around 34 million years ago, Antarctica became encircled by the Antarctic Circumpolar Current. That uninterrupted ring of cold water blocked warmer currents from reaching the continent. Ice sheets expanded across the landmass and remained through every season. Snow compressed into glaciers, glaciers thickened into continental ice, and a permanent frozen reservoir formed at the bottom of the planet. At the same time, another system was quietly shaping the climate from above. Earth's orbit does not remain perfectly constant. Over immense spans of time, subtle variations alter the way solar energy reaches the planet. These oscillations, known as Milankovitch cycles, include changes in orbital shape, axial tilt, and planetary wobble. The cycles existed long before the breakup of Pangea, but only after the continents reached their modern arrangement did those variations become capable of driving large glacial advances and retreats. Approximately 2.6 million years ago, the modern glacial cycle intensified. By then, the Isthmus of Panama had closed, altering ocean circulation between the Atlantic and Pacific. Moisture transport changed. Northern snowfall increased, and immense ice sheets began expanding repeatedly across the higher latitudes of the northern hemisphere. Among the largest was the Laurentide ice sheet, which buried much of North America beneath ice several kilometers thick during glacial maxima. The glacier moved slowly across the continent like a grinding geological tide, carving basins that later filled with water to become the Great Lakes. It reshaped drainage systems, flattened terrain, and left behind vast fertile soils that still define the agricultural heartlands of North America today. Sea levels fell dramatically during these colder intervals because enormous volumes of water became trapped inside continental ice sheets. Coastlines shifted outward. The English Channel disappeared, replaced by open land connecting Britain to continental Europe. Farther north, another land bridge emerged across the Bering Strait. Beringia connected Asia and North America, allowing animals and eventually humans to move between continents during periods of lowered sea level. During the last glacial maximum, approximately 20,000 years ago, ice covered northern Europe, most of Canada, and broad regions of Asia. Human populations adapted continuously to fluctuating climates, changing vegetation, and migrating animal herds. In Africa, repeated shifts between wetter and drier periods altered habitats across immense regions, encouraging movement, flexibility, and technological innovation among early hominin populations. The slow pulse of advancing and retreating ice therefore belongs to a much older tectonic story. The rearrangement of continents after Pangea created the oceans, currents, and polar geography that allowed the modern Ice Age world to exist at all. Far beneath the surface of the modern oceans lies a landscape no human civilization has ever fully seen. Mountains longer than continents cross the abyssal plains. Volcanic ridges glow with geothermal heat, and layers of sediment settle slowly through the darkness year after year. Hidden within that submerged world is a record of Pangea's fragmentation, so precise that geologists can reconstruct ancient oceans almost step by step. The seafloor itself preserves the motion of continents. Along mid-ocean ridges, molten rock rises continuously from the mantle and cools into new oceanic crust. As that magma solidifies, tiny iron-bearing minerals inside the rock align with Earth's magnetic field like microscopic compass needles, frozen in place. The remarkable detail is that Earth's magnetic field reverses periodically. Magnetic north becomes south, and south becomes north over immense intervals of geological time. Because of this, the seafloor forms alternating bands of magnetic orientation. One stripe records normal polarity, the next reversed polarity, then normal again. These paleomagnetic stripes appear on both sides of spreading ridges in nearly perfect symmetry. The Atlantic Ocean floor therefore resembles a gigantic mirrored barcode extending outward from the mid-Atlantic ridge, silently documenting how quickly the continents separated and how long the spreading continued. The farther from the ridge, the older the crust becomes. Near the spreading centers, the seafloor is geologically young. Farther away, it ages gradually until eventually descending beneath another tectonic plate through subduction. Because oceanic crust is constantly recycled into the mantle, very little ancient seafloor survives. The oldest known oceanic crust on Earth, found in parts of the western Pacific, is approximately 280 million years old. Almost everything older has already vanished back into the planet's interior. Above this moving crust, sediments accumulate continuously. Tiny particles of clay, volcanic ash, microscopic skeletons, and drifting organic material settle slowly through the water column onto the deep ocean floor. Over millions of years, these sediments build layered archives, preserving records of changing climate, ocean chemistry, and biological productivity. Scientific drilling programs have extracted long cylindrical cores from these deposits, allowing researchers to read ancient environmental conditions almost year by year. Embedded within the sediment are microscopic organisms called foraminifera and coccolithophores. Their shells preserve chemical signatures that reveal past ocean temperatures and atmospheric composition with astonishing precision. Through these microfossils, scientists can reconstruct warming events, cooling periods, and mass extinctions stretching back tens of millions of years. Deep sea exploration also revealed something entirely unexpected along spreading ridges. In regions where seawater seeps downward through cracks in the crust and encounters magma heated rock, hydrothermal vents form. Superheated, mineral rich water erupts back into the ocean, creating towering vent structures surrounded by ecosystems unlike any previously known. Some vents, called black smokers, release dark plumes rich in sulfide minerals. Others, known as white smokers, emit lighter mineral deposits with different chemical compositions and cooler temperatures. Around both systems, live organisms sustained not by sunlight, but by chemical energy derived directly from Earth's interior. Giant tube worms, specialized bacteria, blind crustaceans, and unusual mollusks survive entirely through chemosynthesis in perpetual darkness. The seafloor records catastrophe as faithfully as creation. Layers rich in iridium mark the boundary of the Chicxulub impact across oceans worldwide, while volcanic ash horizons preserve eruptions separated by continents and ages. Every spreading ridge, sediment layer, and buried magnetic stripe forms part of a planetary archive written slowly beneath the sea, preserving the long memory of a world still drifting apart. Long before satellites measured continents drifting apart, and long before ships mapped the hidden mountains of the seafloor, the idea that Earth's landmasses could move seemed almost absurd. Continents were assumed to be permanent fixtures, rooted immovably to the planet beneath them. Yet, scattered across different fields of science were clues that refused to remain silent. The coastlines themselves offered the first unsettling suggestion. South America and Africa appeared to fit together with strange precision, as though separated pieces of an older structure. Fossils of identical ancient organisms appeared on continents divided by entire oceans. Mountain belts aligned across opposite sides of the Atlantic, and layers of rock matched one another in age and composition, despite thousands of kilometers of separation. In 1912, a German meteorologist named Alfred Wegener gathered these clues into a single radical proposal. He argued that the continents had once formed a connected supercontinent and later drifted apart over geological time. Wegener was not trained as a geologist, which made the scientific establishment even more skeptical of his claims. To many researchers, the idea sounded impossible, yet the evidence continued accumulating around him. Fossils of the seed fern Glossopteris appeared across South America, Africa, India, Antarctica, and Australia. Ancient glacial scratches crossed now tropical continents in directions that only made sense if the land masses had once been joined. Entire mountain systems aligned like broken seams across oceans. The central problem, however, remained unanswered. Wegener could describe the movement, but not the force behind it. Critics demanded to know how continents could possibly move through solid oceanic crust. Without a convincing mechanism, continental drift was dismissed by much of the geological community as speculation rather than science. Wegener continued defending his theory despite widespread rejection. In 1930, during an expedition across the Greenland ice sheet, he died in the Arctic cold before seeing his ideas accepted. For decades afterward, continental drift remained largely marginalized, discussed by only a minority of scientists willing to consider it seriously. The missing answer finally emerged from the oceans themselves. During the 1950s and 60s, improved sonar mapping revealed enormous mountain chains running through the middle of the world's oceans. At nearly the same time, researchers studying Earth's magnetic field discovered the alternating magnetic stripes preserved within seafloor basalt. These patterns demanded explanation. In 1962, American geologist Harry Hess proposed the concept of seafloor spreading. New oceanic crust, he argued, forms continuously along mid-ocean ridges as magma rises from the mantle. Older crust then moves outward and eventually descends back into the mantle at subduction zones. Continents were not plowing through static ocean floor. Instead, both continents and oceanic crust moved together as parts of larger tectonic plates. 1 year later, Fred Vine and Drummond Matthews demonstrated that the magnetic stripes on either side of mid-ocean ridges formed symmetrical mirror patterns exactly matching predictions from seafloor spreading. The ocean floor itself had become direct physical evidence of planetary motion. The effect on geology was immediate and transformative. By the late 1960s, plate tectonics had become the unifying framework of Earth science. Continental drift moved from rejected fringe theory to foundational scientific principle within less than a decade. Today, satellites orbiting high above Earth measure tectonic movement directly. GPS instruments confirm that North America and Europe continue separating by approximately 2.5 centimeters per year. The Atlantic Ocean is still widening, exactly as the rocks, fossils, and magnetic patterns had quietly recorded all along. Far from the quiet widening of the Atlantic, another remnant of Pangea's rearrangement circles the Pacific in almost continuous unrest. Along the edges of the world's largest ocean, the crust bends, fractures, sinks, and melts in an immense chain of geological violence that never truly stops. Volcanoes rise from the sea, mountains rupture upward, entire coastlines shift within minutes. The modern Earth still carries the tension released when the supercontinent began to tear apart. This region is known as the Ring of Fire, a roughly 40,000-kilometer arc surrounding the Pacific Basin. Nearly 90% of the world's earthquakes occur along this boundary system, along with approximately three-quarters of all active volcanoes. The shape resembles a broken horseshoe wrapped around the ocean, tracing the edges where tectonic plates collide and descend back into the mantle. At the center of this system lies the Pacific Plate itself, the largest tectonic plate on Earth, spanning approximately 103 million square kilometers. Unlike the Atlantic Basin, where plates move apart and create new crust, much of the Pacific margin is dominated by destruction. Dense oceanic crust slides beneath lighter continental or island crust in a process called subduction. As the descending slab sinks deeper into the mantle, heat and pressure release water trapped within the rock. The surrounding mantle partially melts, feeding chains of volcanoes above. Japan exists because of this process. The islands are not fragments of an ancient continent, but volcanic arcs raised by the subduction of the Pacific and Philippine plates beneath the Eurasian plate. Every eruption, every trembling city, every tsunami warning emerges from forces operating deep below the ocean floor. The shape of the archipelago itself reflects millions of years of compression, uplift, and rupture along converging plate boundaries. On the opposite side of the Pacific, another fault system waits beneath the forests and coastline of northwestern North America. The Cascadia subduction zone stretches from northern California to British Columbia, where the Juan de Fuca plate disappears beneath the continent. Geological evidence, preserved in drowned forests and offshore sediments, reveals that the region is capable of producing earthquakes exceeding magnitude 9. The last great rupture occurred in 1700, sending a tsunami across the Pacific toward Japan. In 2011, the Tohoku earthquake demonstrated how suddenly tectonic strain can reshape the surface of Earth. The magnitude 9.0 rupture shifted parts of Japan's main island approximately 2.4 meters eastward and altered the distribution of mass within the planet enough to slightly affect Earth's rotational axis. The motion was measurable from space, a brief release of energy accumulated over centuries. Not all volcanic systems along the Ring of Fire form at plate boundaries. Beneath Yellowstone, a mantle plume rises from deep within Earth, feeding enormous magma reservoirs below the crust. This hotspot has produced three super eruptions over the past 2.1 million years, the most recent occurring approximately 640,000 years ago. The landscape of geysers, hot springs, and steaming ground visible today is the quiet surface expression of heat still gathering below. Farther west, the Hawaiian Islands record movement in another way. The hot spot beneath Hawaii remains relatively stationary, while the Pacific Plate drifts northwest above it. Each volcano forms, grows, then slowly moves away as a newer island rises behind it. The chain preserves a chronological trail of volcanic rock stretching across the ocean floor, a moving record of tectonic motion written directly into the Pacific itself. Beneath modern cities, railways, ports, and power grids lies the compressed memory of vanished worlds. Ancient forests became fuel, buried oceans became reservoirs of oil and gas. Mountain collisions concentrated metals deep within fractured crust. The industrial age did not emerge from resources scattered randomly across the planet. It emerged from geological processes set in motion during the assembly and breakup of Pangea. Coal formed first, during the Carboniferous period more than 300 million years ago. Vast equatorial forests spread across humid lowlands near the center of the forming supercontinent. In swampy environments where oxygen was limited, fallen vegetation accumulated faster than it could decay. Over immense spans of time, these buried layers compressed into coal. The coal seams mined in Pennsylvania, Yorkshire, and Germany's Ruhr Valley were once part of the same connected forest system before the Atlantic Ocean separated them. Oil and natural gas formed later within shallow seas that flooded continental margins during and after Pangea's fragmentation. Warm marine environments filled with microscopic plankton accumulated thick layers of organic sediment on the sea floor. When buried beneath newer sediments, heat and pressure gradually transformed this material into hydrocarbons. The petroleum reserves beneath the Persian Gulf originated in the warm waters of the ancient Tethys Sea, while deposits beneath the Gulf of Mexico formed within the inland seaways that once divided North America. The Middle East became exceptionally rich in oil because several geological conditions aligned in the same region. Thick organic sediments accumulated in warm, shallow water then became buried beneath impermeable rock layers that trapped the hydrocarbons below. Heat associated with nearby tectonic activity, including the collision of India into Asia, accelerated the conversion of organic matter into petroleum. The extraordinary concentration of oil was not accidental. It was the product of a specific tectonic and climatic history unfolding over tens of millions of years. Diamonds formed even deeper within Earth, far below the continents. Carbon crystallized under enormous pressure inside the mantle. Violent kimberlite eruptions later carried those crystals upward through ancient continental cores called cratons. Many major diamond deposits, including those in South Africa and Siberia, occur within stable fragments of crust connected to the ancient geography of Gondwana and earlier supercontinents. Along the western margin of South America, the same subduction processes that raised the Andes Mountains also concentrated copper and gold. As the Nazca Plate descended beneath the continent, heated fluids circulated through fractured rock and deposited dissolved metals into enormous ore systems. Chile now produces roughly 28% of the world's copper from deposits created by this long tectonic interaction. The Appalachian coal fields preserve another direct legacy of Pangea's assembly. The collision that built the mountains also buried thick accumulations of organic material from ancient forests. Much of the electricity historically generated across the eastern United States came from carbon locked away during that collision hundreds of millions of years earlier. Even rare earth elements used in electronics and renewable energy technologies reflect the geological consequences of continental breakup. Deposits in Australia and Greenland, formed through unusual volcanic and rifting processes associated with Gondwana's fragmentation. The modern distribution of resources is therefore a geological map of ancient Earth. Every oil basin, coal seam, diamond field, and metal deposit preserves part of the long tectonic story that began when the continents still moved together as one world. Long before cities, agriculture, or language, the ground beneath eastern Africa was already shifting apart. Valleys deepened slowly through the crust. Volcanoes rose along fault lines. Lakes formed inside sinking basins and remained for millions of years before changing shape again. Human evolution unfolded inside a landscape that never stayed still for very long, shaped continuously by tectonic forces inherited from the breakup of Pangea. Africa occupied a unique geographic position in the fragmented world that followed. The continent remained near the equator and bordered major ocean systems on multiple sides, exposing it to repeated climatic oscillations during the ice ages of the late Cenozoic. Rain belts shifted north and south over immense spans of time. Forests expanded during wetter intervals, then retreated as grasslands spread across eastern and southern Africa. Early hominins survived within environments that changed repeatedly across relatively short geological periods. At the same time, the crust beneath eastern Africa was beginning to split. The East African Rift System stretches from the Afar Triangle in Ethiopia southward toward Mozambique, forming one of the clearest modern examples of continental rifting on Earth. The land slowly thins as tectonic forces pull the region apart. Earthquakes and volcanic eruptions remain common along the rift today, reminders that the process is still active beneath the surface. This geological instability created an unusual patchwork of habitats: forest, savanna, volcanic highlands, lake shores, and seasonal rivers often existed close together. Early hominins moving through these environments encountered rapidly shifting conditions that favored adaptability over specialization. Dietary flexibility, tool use, and mobility became increasingly valuable traits in landscapes where water sources and vegetation patterns could change dramatically over time. The oldest known hominin fossils come directly from this tectonically active region. Ardipithecus, dating to approximately 4.4 million years ago, was discovered in Ethiopia within the Rift System. Australopithecus afarensis, including the famous skeleton known as Lucy, lived roughly 3.2 million years ago within similar environments shaped by volcanism and shifting climate. Later species, such as Homo habilis, also emerged in eastern Africa as tectonic activity continued restructuring the terrain around lakes and valleys. The rift itself created some of the deepest freshwater systems on Earth. Lakes, Turkana, Tanganyika, and Malawi occupy elongated basins formed by crustal stretching and faulting. Their sediments preserve fossils, pollen, volcanic ash, and chemical records extending back millions of years. These lake systems became natural archives of environmental change, preserving much of the evidence used to reconstruct human origins. Lake Tanganyika became especially remarkable because of its age and depth. Reaching approximately 1,470 meters deep and existing for roughly 9 to 12 million years, it evolved in long isolation. Entire groups of endemic fish diversified within its waters, creating ecosystems found nowhere else on Earth. The lake functions almost like a freshwater island world, produced not by oceanic separation, but by tectonic rifting. Far to the north, another geological consequence of Pangea's fragmentation later shaped human migration. Antarctic glaciation lowered global sea levels during ice ages, exposing Beringia, the land bridge connecting Siberia and Alaska. Human populations eventually crossed this corridor into the Americas during periods when ocean water remained locked within massive continental ice sheets. The modern arrangement of continents therefore shaped not only where humans evolved, but how humanity spread across the planet. Africa's central position, the isolation of Australia, and the temporary exposure of northern land bridges all emerged from tectonic movements that began hundreds of millions of years before the first humans appeared. The continents appear permanent only because human history is brief. Beneath the oceans and mountain ranges, the plates continue moving with the same slow persistence that once assembled Pangea and later tore it apart. The Atlantic still widens, the Pacific still contracts, Africa continues pressing northward into Europe, Australia drifts steadily toward Asia. The world map hanging in classrooms today is only a temporary arrangement inside a cycle that has repeated for more than 1 billion years. Geologists can project many of these motions far into the future because plate movement follows measurable patterns over immense spans of time. Using seafloor, spreading rates, subduction zones, and satellite measurements, scientists have modeled possible continental arrangements roughly 250 to 300 million years from now. The details remain uncertain, but the broader trend appears unavoidable. Earth is likely moving toward another supercontinent. One proposed future configuration is called Pangea Proxima, sometimes known as Pangea Ultima. In this model, the Atlantic Ocean eventually stops widening and begins to close. North and South America drift back eastward toward Europe and Africa, reconnecting continents that separated during the Jurassic and Cretaceous periods. The resulting supercontinent would occupy roughly the same broad region where Pangea once existed, though the mountain ranges, coastlines, and climates would be entirely different. Another model proposes a very different destination. In the scenario called Amasia, the Pacific Ocean closes instead of the Atlantic. The Americas drift westward and northward, eventually colliding with Asia near the Arctic region. Rather than forming around the equator, the next supercontinent would gather near the North Pole, fundamentally altering global climate and ocean circulation. Although the Atlantic continues widening today, small subduction systems already exist along portions of its margins. The Caribbean region and the Scotia Arc near Antarctica show early signs of oceanic crust beginning to descend beneath surrounding plates. If these zones expand over tens of millions of years, the Atlantic could eventually reverse from growth to contraction. Meanwhile, the Pacific steadily shrinks. Its ocean floor disappears into subduction zones around much of the Ring of Fire at a rate of roughly 2.5 centimeters per year. Over several hundred million years, this continual destruction of oceanic crust may eliminate the Pacific basin almost entirely. Australia is already moving northward faster than any other major tectonic plate, advancing approximately 7 centimeters each year. Within 50 to 100 million years, the continent is expected to collide more completely with Southeast Asia. Mountain ranges will rise along the collision zone, while ocean circulation through the Indonesian region changes dramatically. Africa's movement toward Europe continues as well. The Mediterranean Sea, itself, the last remnant of the ancient Tethys Ocean, will eventually close completely. As compression intensifies, the Alps may rise again, while entirely new mountain systems could emerge across southern Europe and North Africa. The climate of the next supercontinent may resemble the harsh extremes that once dominated Pangea. Vast continental interiors, far from moderating oceans, could experience severe seasonal swings, immense desert belts, and enormous monsoon systems. Ocean circulation would reorganize once again, redistributing heat across the planet in unfamiliar ways. The world humans know therefore exists only within a temporary interval of Earth's tectonic rhythm. The continents are still traveling, still colliding, still separating, carrying the future shape of the planet silently beneath our feet. Long before Pangea formed, the Earth had already assembled and broken apart entire worlds. Continents drifted together, fused into immense landmasses, then fractured again into scattered fragments surrounded by widening oceans. The process unfolded so slowly that mountains rose and vanished between each phase. Entire branches of life appeared, flourished, and disappeared without witnessing a complete cycle. Pangea was not the beginning of this pattern, only the most recent version, still visible in the rocks beneath our feet. Geologists now understand that the planet follows what is called the supercontinent cycle, a recurring sequence lasting roughly 300 to 500 million years. Continents gradually converge through plate motion, assemble into a supercontinent, remain joined for immense stretches of time, then break apart once more as heat accumulates beneath the crust. Ocean basins open and close. Climate systems reorganize. Evolution changes direction. One of the best known predecessors to Pangea was Rodinia, assembled around 1.1 billion years ago. Its geography looked nothing like the modern Earth. Vast continental masses clustered near the equator, while oceans occupied entirely different regions of the globe. When Rodinia eventually fragmented, the rearrangement of land and sea may have destabilized the climate so severely that Earth entered one of the strangest periods in its history. Around 720 million years ago, and again near 635 million years ago, the planet may have experienced what scientists call snowball Earth conditions. Ice possibly extended from the poles toward the equator. Some models suggest oceans froze to depths of hundreds of meters beneath a pale atmosphere, reflecting sunlight back into space. Glaciers may have covered regions that are tropical today, while volcanic activity continued beneath the ice and darkness. Yet life endured. Evidence suggests photosynthetic organisms survived in isolated refuges where volcanic heat or thin ice allowed liquid water and faint sunlight to persist. Around hydrothermal systems and fractured coastlines, tiny surviving populations carried the continuity of life through conditions that would have once seemed impossible. Every forest, reef, bird, and mammal alive today traces its ancestry through those scattered refuges hidden within a frozen world. Even older than Rodinia was another probable supercontinent known as Columbia or Nuna, assembled roughly 1.8 billion years ago. During that distant era, the atmosphere itself was changing. The Great Oxidation Event, which had begun earlier, around 2.4 billion years ago, slowly transformed Earth's chemistry as photosynthetic microbes released increasing amounts of oxygen into the oceans and sky. The breakup of these ancient continental systems altered weathering patterns, ocean circulation, and nutrient delivery, helping establish conditions that eventually allowed complex, multicellular life to evolve. Across each supercontinent cycle, a repeating pattern appears. Assembly creates continental interiors vulnerable to drought, temperature extremes, and ecological stress. Breakup reshapes coastlines, opens shallow seas, alters ocean currents, and isolates populations. Extinction follows instability, yet recovery repeatedly produces bursts of evolutionary innovation as surviving organisms expand into newly available environments. Pangea's story, therefore, belongs to a rhythm far older than dinosaurs, mountains, or mammals. The Earth itself moves through cycles of gathering and dispersal, compression and release, silence and renewal. Continents drift like slow currents within a deeper planetary pulse that has continued for billions of years, long before humanity appeared to notice it. Most people experience the Earth as permanent. Streets remain where they were built. Mountains appear motionless. Coastlines seem fixed against the sea. Yet every city, river, and valley exists inside a planetary system that has never stopped rearranging itself. The continents beneath modern civilization are still drifting, colliding, stretching, and breaking apart exactly as they did in the distant ages before humans appeared. Some of humanity's largest cities stand directly atop active tectonic boundaries. Los Angeles lies along the San Andreas Fault, where the Pacific Plate slides northward against the North American Plate at several centimeters each year. The movement is slow enough to escape ordinary notice, yet the accumulated strain periodically releases in violent earthquakes. In 1906, San Francisco was devastated when the fault ruptured across Northern California. Entire districts collapsed or burned. Far across the Pacific, Tokyo occupies an even more unstable position near the junction of multiple tectonic plates descending beneath one another beneath the Japanese archipelago. The ground beneath millions of people shifts constantly, even during apparent stillness. Farther west, the immense glaciers of the Himalayas store frozen water created by the collision between India and Asia. Snowfall gathers across peaks that did not exist before the continents met, then slowly melts into rivers that sustain nearly 2 billion people. The Ganges, Indus, Yangtze, Yellow, Mekong, and Irrawaddy all depend upon mountain systems lifted upward by tectonic compression over tens of millions of years. As modern warming accelerates glacial retreat, the stability of these freshwater systems becomes increasingly uncertain, linking ancient geology directly to the present human condition. Across North America, the extraordinary fertility of the Midwest also traces back to planetary motion. During the Great Ice Ages, vast glaciers spread southward from the Laurentide ice sheet, grinding stone into fine sediment and redistributing mineral-rich soil across immense plains. When the ice finally retreated, it left behind some of the most productive agricultural land on Earth. The farms feeding modern cities exist because Antarctica became isolated millions of years ago, allowing glacial cycles to intensify across the northern hemisphere. In South Asia, Bangladesh occupies the immense Bengal Delta, a landscape continuously rebuilt by sediments washing down from the Himalayas. Rivers descending from those mountains carry pulverized rock across the plains before depositing it into low coastal regions near the Bay of Bengal. One of the most densely populated places on Earth, therefore, exists because India traveled northward across an ancient ocean and struck Eurasia with enough force to raise an entire mountain system toward the sky. Around the Pacific, millions of people inhabit some of the most geologically unstable regions on the planet. Japan, Indonesia, the Philippines, and the Pacific Northwest all lie within the Ring of Fire, where oceanic crust descends back into the mantle beneath volcanic arcs and coastal mountain chains. Earthquakes, eruptions, and tsunamis remain part of ordinary existence in these regions because the forces that once fragmented Pangea are still active beneath the oceans. Even the industrial age emerged from ancient geography. Much of the modern world was powered by oil formed within vanished seas that existed when continents occupied entirely different positions. The energy driving factories, aircraft, and cities came from organisms buried in warm marine basins millions of years before humans evolved. We live, often unknowingly, within the continuing motion of a planet that has never been still, beneath the continents, beneath the oceans, beneath every fault line and mountain chain described throughout this story. There is still a region humanity has barely touched. The Earth's interior governs the movement of continents, feeds volcanoes, bends magnetic fields, and drives the slow machinery of plate tectonics, yet almost all of it remains physically unreachable. Compared to the deep crust and mantle, the surface where human civilization exists is thinner than frost on stone. The deepest hole ever drilled by humans lies on the Kola Peninsula in northwestern Russia. For 24 years, engineers and geologists pushed deeper into the crust, eventually reaching a depth of 12,262 meters before the project ended in 1992. Even after decades of drilling, the borehole had penetrated only about 0.2% of the distance to Earth's core. At those depths, temperatures rose far beyond expectations. Rock behaved less like solid stone and more like softened plastic under immense pressure. The deeper machinery of the planet resisted entry. What the drillers discovered challenged long standing assumptions. Geologists expected a transition from granite to basalt several kilometers below the surface, inferred from seismic wave behavior, yet the boundary never appeared. Instead, the crust remained compositionally complex, far deeper than predicted. Water was also discovered within fractures at depths once thought impossibly dry. Locked inside minerals and compressed rock, it revealed that even the deep crust contains hidden reservoirs moving slowly through ancient stone. Beyond the crust lies the mantle, extending nearly 3,000 kilometers downward. No human instrument has directly sampled most of it. Everything known about this immense region comes indirectly from volcanic eruptions carrying fragments upward, from seismic waves traveling through earthquakes, and from laboratory simulations recreating pressures found deep inside the Earth. The mantle is understood more through echoes and distortions than direct observation. Modern geophysics uses seismic tomography to map the interior, almost like a planetary medical scan. Earthquake waves bend, accelerate, or slow depending on the material they pass through, allowing scientists to reconstruct structures hidden far below the surface. These images reveal cold slabs of oceanic crust sinking into the mantle after subduction, while enormous plumes of hotter material rise upward toward the crust. Yet even these maps contain unexplained regions. Near the boundary between the mantle and core are two immense formations known as large low-shear velocity provinces. One lies beneath Africa, the other beneath the Pacific Ocean. Each is continental in scale, towering upward from the deep mantle like submerged geological continents hidden inside the Earth itself. Their composition remains uncertain. Some researchers suspect they are accumulations of ancient subducted crust. Others propose they may contain material left from the colossal collision that formed the Moon billions of years ago. Even the origin of plate tectonics remains unresolved. Earth appears unique among nearby rocky planets. Venus is similar in size and composition, yet lacks moving plates. Water deep within Earth's mantle is currently considered one of the leading explanations, weakening rock enough to allow tectonic motion, though the full process remains uncertain. The planet therefore continues to hold silence beneath everything we know. Every earthquake, deep drilling project, and volcanic eruption briefly illuminates another fragment of the hidden system below us, then leaves new mysteries behind in the darkness again. Seen from orbit, the continents appear calm. Coastlines curve gently beneath clouds. Oceans hold their familiar shapes. The planet turns in silence against the darkness of space, giving almost no outward sign that the surface is continuously shifting beneath the atmosphere. Yet Earth is not static in the way the Moon is static, nor frozen like Mars. Beneath the thin skin of crust, the interior remains active, circulating heat upward through moving plates and drifting continents. Among the known planets of the solar system, Earth appears unique in possessing active plate tectonics on a global scale. Venus bears scars of volcanism but lacks the mobile plates shaping Earth's surface. Mars once held internal heat strong enough to power giant volcanoes, yet its crust eventually settled into stillness. Here alone, continents migrate across the globe while ocean basins open and close in cycles lasting hundreds of millions of years. Mountains rise, erode, and rise again in different forms. The geography familiar to human civilization is temporary, part of an ongoing rearrangement too slow for ordinary perception. This motion does more than reshape landscapes. It regulates the stability of the climate itself. Deep beneath the oceans, volcanic systems release carbon dioxide into the atmosphere through outgassing, while weathering across continents gradually removes that carbon and locks it into rock and sediment. Through subduction, some of that buried carbon descends back into the mantle before eventually returning through volcanism once more. This long carbon silicate cycle functions as a planetary thermostat operating across immense spans of geological time. Without that recycling, Earth might have drifted toward climatic extremes. A permanently frozen world can reflect sunlight until oceans remain locked beneath ice for millions of years. A runaway greenhouse can trap heat so effectively that surface water disappears entirely into the atmosphere. Scientists suspect variations of these outcomes may have overtaken Mars and Venus long ago. Earth remained habitable partly because tectonic activity continuously adjusted atmospheric chemistry, while continents moved across changing latitudes. Life itself became intertwined with this geological engine. Plants and microorganisms accelerate the weathering of rock, drawing carbon dioxide from the air while breaking minerals apart. Rivers transport those minerals toward the oceans, where marine organisms incorporate them into shells and sediments. Tectonic uplift then exposes fresh rock to erosion again. Biology and geology therefore became linked systems, influencing one another across billions of years, each subtly modifying the other's future. The arrangement of continents at any moment also determines the pathways available to evolution. Oceans isolate populations, mountain ranges redirect rainfall and winds, inland seas divide ecosystems, while land bridges reconnect them. The breakup of Pangea produced isolated evolutionary regions, altered ocean circulation, and reshaped climates in ways that eventually created the environmental conditions within which human beings evolved. Even the seven continents recognized today are not fixed entities. They are temporary fragments moving through a larger cycle that began long before humanity existed and will continue long after modern nations disappear. The ground beneath every city has occupied different climates, different latitudes, and different worlds across deep time. Ancient seabeds became deserts, polar ice once covered fertile plains, forests buried in vanished swamps became coal beneath modern mountains. The pale blue dot drifting through space is not merely inhabited, it is active, unfinished, and still in motion beneath everything we know. At first glance, this can seem like a story made entirely of measurements, distances between continents, temperatures locked inside stone, ages calculated from radioactive decay, layers of sediment stacked quietly beneath oceans. Yet, beneath all of those measurements lies something larger, a narrative stretching across such immense spans of time that even mountains become temporary features within it. The breakup of Pangea began before the first true dinosaurs spread across the continents. It continued while giant reptiles ruled inland floodplains and shallow seas. It continued while flowering plants transformed forests, while mammals inherited the world after extinction, while glaciers advanced and retreated across the northern hemisphere. It is still continuing now, beneath cities lit by electricity and satellites orbiting overhead. Few events in the history of complex life have lasted so long or reshaped so many futures at once. Every mountain range carries the memory of motion. Stone that now stands above the clouds was once compressed between drifting landmasses, unable to remain apart or together peacefully. The Himalayas continue rising because India still presses northward into Eurasia. The Andes climb along the western edge of South America because oceanic crust continues descending beneath the continent. Even older ranges, softened by erosion and covered in forests, preserve the remains of collisions so ancient that the oceans involved no longer exist. The oceans themselves are equally temporary. The Atlantic feels permanent only because human history occupies such a narrow moment in geological time. Yet it began as a fracture opening gradually through the crust of Pangea, widening year by year as magma rose between separating continents. Every ocean basin records an earlier separation. Every coastline marks the edges of continents still drifting away from former neighbors. Life evolved within this moving architecture. The Amazon rainforest exists partly because South America drifted into a latitude where warm moisture could circulate inland, while the rise of the Andes redirected winds and trapped rainfall across an immense basin. Without those tectonic movements, the forest would never have formed in its present state. The same pattern extends across the world. Isolated continents became evolutionary laboratories separated by oceans and mountains, producing distinct animals, plants, and ecosystems that could not have emerged within a single connected landmass. The immense diversity of life on Earth, therefore, reflects fragmentation as much as continuity. Hundreds of thousands of flowering plants, insects, birds, and mammals evolved partly because populations became separated long enough to follow different evolutionary paths. Isolation created divergence. Divergence created complexity. The living world surrounding humanity today emerged from countless ancient separations unfolding across drifting continents. There is a quiet symmetry in that process. Pangea assembled through collision and later fragmented through tension, yet both phases generated transformation. Mountains rose from compression. Oceans formed from rupture. Extinction cleared ecological space, while isolation allowed entirely new forms of life to appear. The Earth repeatedly turned separation into diversity. And beneath the present world, the motion continues. The Atlantic widens by centimeters each year. Australia moves steadily northward. Africa presses toward Europe. Deep beneath Asia, India continues driving into the continent that stopped its long oceanic journey. This story never truly reached an ending. The continents are still traveling through it now, and so are we.